Hello guys, in this video we're going to learn about electrochemistry. We will be revising full theory of electrochemistry.
First topic of electrochemistry is conductivity. Conductivity. What is conductivity? Conductivity is the ability of a material to flow current through it. Let's write it down. Ability of a material to flow current through it. The next one is resistance. What is resistance? Resistance means blocking something. Now let's derive an expression for resistance. Resistance R is directly proportional to the length and R is inversely proportional to the area. Resistance is inversely proportional to the area. If the length increases, R increases, resistance increases. If the area decreases, the resistance increases. And we'll form a equation. R equal resistivity. This is a constant resistivity into L divided by A, and this is resistivity, and this is length of the conductor. This is area of the conductor. This is resistivity of the material, length of the conductor, area of the conductor. This is resistance. Now let's look at what is conductance. 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 Conductance means we symbolize it by G, 1 over R. The conductance is inversely proportional to R. Conductance is 1 over R. Conductance means opposite of resistance. Resistance means opposite of conductance. And with the resistance we symbolize by ohm. Resistance we symbolize by ohm. And here we symbolize conductance by Siemens. S-I-E-M-E-N-S, Siemens. Here we have something called resistivity, and in conductance we have something called as conductivity. And conductance, we can write this as, what is resistivity? Resistance equal rho L over A, right? Here A over rho L. We represent conductivity as 1 over rho. This is conductivity. 1 over rho. This is conductivity. Here we give a symbol for this is K A over L, and this is conductance, and this is conductivity. That K is equal to 1 over rho. And the conductivity and resistivity. Conductivity K, comma, rho, resistivity, they are constant. Are constant in a metal or an ionic solution. An ionic solution with known concentration. Ionic solution with known concentration. The conductivity factors affecting the conductivity. Now let's look at the factors affecting the conductivity. Factors affecting the conductivity. There are three factors affecting the conductivity. First factor, nature of the solute. Nature of the solute. Second one, concentration of the solute concentration. And the third one, temperature. Third one is temperature. Temperature of the solution. There are two types of conductors. First, electrical conductors, and the second one is ionic conductors. In electrical conductor, electricity is conducted by here they are conducted by flow of electrons, and here in ionic conductors they are conducted by flow of ions. Flow of ions. If we consider solutions, they can be categorized into three types. First, strong electrolyte, weak electrolyte, and non-electrolytes. Non-electrolytes are insulators and particular substance fully ionized. If a particular substance is fully ionized, it is a strong electrolyte. It can be a strong acid, strong base, or it can be an ionic solid. Let's write it down. There are three types of solution. First one, strong electrolyte. Second one, weak electrolyte. And the third one is non-electrolyte. These strong electrolytes are fully ionized. They are fully ionized, and weak electrolytes are partially ionized. And non-electrolytes are insulators. They don't undergo ionization. The strong electrolyte, examples of strong electrolytes are solid ionic compounds, and strong acid, strong base. And weak electrolytes can be taken as weak acids, weak bases. The non-polar electrolytes are non-polar organic compounds. They are non-polar organic compounds. Example, benzene, kerosene compounds. Benzene, kerosene, ionic solids, and these are ionic solids. And the strong electrolyte, strong solid electrolytes, there is a point, strong solid electrolyte, strong electrolytes do not conduct electricity. What is the reason? They don't have ions. Due to lack of ions. If they are in a molten state, they conduct electricity. If we consider this, the nature of the solute and concentration of the solution. If the concentration of the solution decreases, conductivity also decreases. Directly proportional to conductivity. So if the solute concentration increases, conductivity increases. And if the temperature increases, conductivity increases. And the nature depends on the, if the size is small, conductivity increases. If the size is small, speed increases, therefore conductivity increases. And that's all for conductivity. The next part is electrodes in equilibrium. We're going to discuss about electrodes. Electrodes is a second chapter of electrochemistry. And previous lesson we learned about conductivity. In our syllabus there are 4 electrodes. We'll be learning about that in this video. I'll be including every important points. Please don't forget to take notes. I hope you're ready. Let's hop into the video. Before learning about electrons in equilibrium, we should learn about the reactivity of metals in a solution. Reactivity of metals in solution. For example, if we place a metal in a solution, I'll take magnesium in aqueous solution. It is in solid state and they form Mg2 plus ions, aqueous, and 2 electrons. Magnesium rod is dipped in the magnesium 2 plus solution. There will be quick buildup in electrons on the magnesium. The magnesium rod will be surrounded by the solution of positive magnesium 2 plus ions, and some of the magnesium 2 plus ions will reclaim their electrons and stick back to the magnesium rod we dipped into the solution. Mg2 plus aqueous solution plus 2 electrons, they form magnesium solid. In our syllabus there are 4 types of electrodes. This electrode means that the system is a system where a metal is in dynamic equilibrium with its ions. A system where a metal is in dynamic equilibrium with its ions. System where a metal is in dynamic equilibrium with its ions. In our syllabus we have 4 types of electrodes. First electrode, metal and metal ion electrode, and the second one is metal insoluble salt electrode, and the third one is gas electrode, and the fourth one is redox electrode. In an electron there could be only, in one electrode there could be only 2 reactions. One, it can attract release electron. 2, it can attract electron. Now let's look at an example. There are two electrodes. One electrode is made up of magnesium and the second electrode is made up of copper. If we consider those, Mg solid forms Mg2 plus 2 electrons, and if we consider Cu solid, they form copper 2 plus and 2 electrons. And these are the reaction that could occur. This is a reversible reaction. This is reaction number 1 and this is reaction number 2. Here one metal will undergo reduction and other metal will undergo oxidation. In this case, the first reaction, the forward reaction is oxidation reaction, and the second one is reduction reaction. Oxidation means releasing electron, reduction means gaining electron. To find the potential of an electrode, we use a reference electrode, which is we called as standard hydrogen electrode. We compare the electrode with another electrode. We use standard hydrogen electrode to compare other electrode with. Okay, let's write it down. Each electrode has different electrode potential. Here we compare the electrode potential with standard hydrogen electrode. Standard hydrogen electrode. And standard electron hydrogen is used in some conditions. The conditions are conditions 1 atm pressure, and it should be the temperature should be 25 degrees Celsius. Temperature should be 25 degrees Celsius. And the concentration of the hydrogen ion, H plus concentration, should be 1 mole dm minus 3. Now let's look at standard hydrogen electrode. This is a solution. This is dipped in the solution, dipped inside a solution, and there will be an equilibrium established between the hydrogen gas and H plus ions by there will be a equilibrium established by the hydrogen molecules and hydrogen ions in the solution, which is catalyzed by the platinum. This is PT, and there will be H plus equals here. Concentration will be 1 mole dm minus 3, and here H2 gas is inserted, and this is a PT wire. Now let's see how we measure the potential of a electrode using standard hydrogen electrode. Let's draw the cell. Okay, this is the structure, and this is magnesium strip, and this is dipped into a solution. These are dipped into the solution, and this is PT, and this is PT wire, and these are conducting wires, and here the H2 gas is inserted, to gas, and this will be a voltmeter. And in this solution there will be magnesium 2 plus ions equals, and here there will be H plus equals, which is 1 mole Dm minus 3, and this is salt bridge. I'll explain what is salt bridge. We use salt bridge to complete the circuit. Which acts as a liquid junction, which forms a liquid junction. And also the salt bridge is just a glass tube filled with a solution such as potassium nitrite. Let's write it down. Glass tube filled with solutions or solution of an electrolyte. It is filled with solution of electrolyte. Solution of electrolyte such as potassium nitrate. One and two. These are points of salt bridge. And each side of the electrodes are called as half cell. And okay, wait, I'll show which is half cell. Okay, if we consider this is a half cell. And if we consider this one is also a half cell. And there is another point in the salt bridge, the content in the salt bridge. And the electrolyte used in salt bridge does not react with salt bridge. The compound which used to form salt bridge doesn't react with either contents in the beaker. How the potential of the electrodes are found? Here they consider the standard hydrogen electrodes potential as 0 voltage, and they are connected, and the voltmeter reading will show the electrode potential of the metal. In this case, the reading will be the potential of magnesium. The voltage reading means it is potential different. Potential of the, hydrogen minus potential of magnesium. And that's how the electrodes potential are found. This standard hydrogen electrode is considered as 0 volts at 1 atm pressure and 25 degrees Celsius and 1 mole Dm minus 3. For example, if we take the above cell, this electrode and this electrode, the voltmeter reading is, in example, 2.37 volts, and the voltmeter shows the reading of magnesium as negative electrode and hydrogen as the positive electrode, and therefore the magnesium 2 plus and magnesium electrode is recorded as minus 2.37. Here the magnesium has a higher ability to form ions than the hydrogen, therefore it is minus electrode, negative electrode. The magnesium 2 plus aqueous over magnesium solid the electrode potential is minus 2.37 volts. One of the electron will undergo reduction and other electron undergo oxidation. And here the magnesium 2 plus undergo reduction because it has the ability to attract electron more than the hydrogen. Now let's see how the electron notations are written. Electrode notations. Electrode notation, PT solid and a dash interface and H2 gas, and it forms H plus aqueous, and these are this line. Vertical line shows the interface between PT and H2 gas, and this interface shows interface between H2 gas and H plus gas. For example, if we write notation for magnesium, let's write notation for magnesium. Magnesium solid, and there will be an interface magnesium 2 plus aqueous, and that's all. There is no any other interfaces. And the next part we're going to look at is metal insoluble salt. Let's look at metal insoluble salts, or which we call as calamine and silver chloride, silver chloride electrode. Metal and insoluble salt electrode, we call it as, there is two electrodes, calamine electrode and silver chloride. Metal insoluble salt electrode. What is metal and insoluble salt electrode? If a metal is in contact with a solid salt of the same metal, such electrodes are called as metal insoluble salt electrodes. So let's write it down. If a metal is in contact with the solid state, solid salt of the same metal is called as metal insoluble salt electrode. Example for these are calamine electrode and silver chloride electrode. In these electrodes, a saturated solution of KCl is used for electrical conductance. Let's write it down. In these electrodes, a saturated solution of KCl is used for electrical conductance, and there will be a PTY also. PT wire is used to establish the electrical conductance. Establish the electrical connection. Now let's do a diagram for calomel electrode and silver chloride electrode. Here, let's draw calomel electrode. Here let's draw silver chloride electrode. This is the calomel electrode and this is the silver chloride electrode. Let's identify the parts. This is a PT wire, platinum wire, and this is a PT electrode. This is the PT electrode, and this in the green color thing is KCl solution. KCl solution. This is saturated KCl solution. Saturated KCl solution. This is also KCl solution. And this one is Ag metal, silver chloride. This is and this part is used to connect the second cell. Used to connect second cell. And this blue color part, this one is mercury liquid, Hg liquid, and this part red dots present, and that part is called as calomel paste. Calomel paste. Calomel paste means Hg2Cl2. This is mercury liquid and this is calomel paste, which is Hg2Cl2. And the tip of the part is called as separator. Tip of the part, mark here, separator. This is calomel paste and this is mercury liquid and this is separator. The separator is used to connect the second cell, and the solution of the calomel electrode and AgCl electrode is saturated KCl solution. Okay, this wire in silver chloride, we use the wire, it is silver wire, Ag wire, and here the electrode is silver chloride salt on silver wire. AgCl salt on silver wire. This part at the bottom, this part is ceramic or quartz, glass fiber, just it's a junction. Ceramic, quartz, fiber, glass fiber inductance junction. And this part is used to connect the cell with the external solution. I'll write it here. Used to connect the cell with, electrode with external solution. In metal ions, we learned that the standard hydrogen electrode is a reference electrode, and we can, in general, the calomel electrode and silver chloride electrode are also known as reference electrodes, as the potential of these electrodes remain almost constant during the experiment time. Their potential is constant during the experiment time. Here we use PT wire. Here we use PT wire. And here we use AG wire. The solutions are same, saturated KCl solution. And here we use PT electrode, and here we use AG silver chloride on silver wire. Use that as the electrode. Here we use separator. Here we have a junction, and there is a calomel paste here. The reaction in silver chloride electrode is AgCl solid plus electron. They form Ag plus, Ag solid plus Cl minus aqueous. The next part we have is gas electrode. Gas electrode. In our syllabus, we have two electrodes. First, hydrogen electrode. Hydrogen electrode, we already learned that. And the next one is chloride electrode. Chloride electrode. This hydrogen electrode is called as standard hydrogen electrode. We know that. Standard hydrogen electrode, and its potential is 0 voltage. Let's look at the reaction. 2H plus aqueous plus 2 electrons. The reversible reaction, they form H2 gas. And now let's look at the chloride electrode. Supposed to be chlorine electrode. And now let's look at the chlorine electrode. Chlorine is a well-known oxidizing agent. It acts as oxidizing agent. It undergoes reduction. And let's look at the reaction. Cl2 gas plus 2 electrons, they form Cl2 gas. Cl2, 2 electrodes, and they form Cl2 gas. Condition should be same. Here 1 mole Dm minus 3, 25 degrees Celsius, 1 atm. Here also it should be 1 mole Dm minus 3. Suppose they have only mentioned the concentration. If you write the notation for chloride electron, the notation will be Pt solid and chloride gas and Cl minus aqueous. Last electrode is redox electrodes. Both oxidized and reduced species are present in that electrode solution. Redox electrode. Let's write it down. Both oxidized and reduced species must be presented in the solution of electrode is called as redox electrode. Here we use, as usual, we use PT wire, platinum wire, for electrical connection, with the external circuit. Now let's look at a iron redox electrode. Iron redox electrode Fe2 plus and Fe3 plus redox electrode. Fe3 plus is reduced to Fe2 plus. Is a reversible reaction. Yes. How these electrodes are created? These electrodes are, the platinum electrode can be inserted into a beaker containing a solution of both iron Fe2 plus and Fe3 plus ions. The concentration should be 1 mole Dm minus T with respect to each other, and couple this to a hydrogen electrode. Let's draw this electrode. Let's draw a redox electrode. This is the Fe2 plus Fe3 plus redox electrode. In this solution, we have Fe2 plus, Fe3 plus solution, which contain Fe3 plus and Fe2 plus. They will be in aqueous form. Here, this one is a PT wire, and this one is a inert metallic electrode. Inert metallic electrode, which is platinum and palladium. Okay, now let's write the notation. Well, there is few rules in electro notation. The first rule is phase boundaries. Phase boundaries are separated by a vertical line. And the second rule is physical states must be included next to each chemical species. if given. Species and condition also should be included. And conditions must be included. For example, let's take a gas electrode. In the gas electrode, there will be PT solid and separated by vertical line, which is the interface, and O2 gas and OH minus aqueous. These are interfaces mentioned. And now let's consider a redox reaction for the second one. Redox electrode, PT solid interface and Fe2 plus, which is aqueous, and the conditions are 1 mole Dm minus 3, whole 3 in bracket, aqueous, 1 mole Dm minus 3, interface Fe3 plus, aqueous, and 1 mole Dm minus 3. If the temperature or atmospheric pressure are given, you should also mention that those. Okay, now let's summarize the type of different electrodes with types of different electrodes with their types of electrodes, standard notation, redox couple, and reduction half reaction. First electrode is metal and metal ion electrode. Metal and metal ion electrode. Standard notation can be written as, if we consider the metal in the interface, Mn plus is aqueous, and the redox couple is solid, metal solid, and metal ion. The half reaction, reduction half reaction is M metal ion plus aqueous plus number in electrons into M solid. And the second electrode is metal insoluble, metal and insoluble salts is M metal solid interface Mx N solid and X minus ion aqueous. And the redox couple is metal solid and salt solid. And the redox reaction is the reduction half reaction is Mx solid plus electron. It forms n number of metal solid plus X minus aqueous. The third electrode is gas electrode. In a gas electrode, there will be a PT solid interface and X2 gas interface, X plus aqueous, and it will form the redox couple is X2 gas, X aqueous, and the redox reaction X plus aqueous plus electron, they form half X2 gas. The last electrode is redox electrode. Redox electrode's notation is Pt solid interface M plus ion aqueous and M2 plus ion aqueous. The redox couple is M plus aqueous M2 plus aqueous. M2 plus aqueous plus electron, they form M plus aqueous. This is the reduction half react. I mark these red lines as to separate them. Take a screenshot if you want. When we are writing the electrode reaction, it should be represented in one single error. Let's consider potassium. If potassium is there, K plus aqueous plus electron is the reduction reaction. They form solid, potassium solid, and this will be represented in single arrow. This means there is a current flowing through. Single arrow means there is a current flowing through. Now let's consider the standard reduction potential of elements, electrodes. When the potential is more negative, the reduction ability increases. Reducing ability increases, undergo oxidization. When the potential is more negative, oxidizing ability increases and they undergo reduction. Let's look at an example. If we consider potassium, there is a potassium solid and potassium ion electrode, and there is a zinc solid and the zinc 2 plus electrode. The potential of the reduction potential of potassium is minus 2.93 volts and zinc's reduction potential is minus 0.73 volts. If we compare these, which is more negative? More negative means this is more negative, which means it undergo oxidization. More negative means they undergo oxidization, and therefore the zinc will undergo reduction if these both are, if the cell contain potassium electrode and zinc electrode. This will be the reaction. Potassium will undergo oxidization and zinc will undergo reduction reaction. Oxidization means they release electron, reduction means they gain electron. More negative means they already have more electrons. Negative means electron has a negative charge. This is an example. They already have more electrons. Therefore, the negative potential will try to oxidize, and the positive ones have less electrons, low number of electrons. Therefore, it will gain electrons. More negative means oxidization. More positive means reduction. And that's all for electrodes. We're gonna revise electrochemical cell. In previous video, we learned about electrodes. Here, we're gonna learn about electrochemical cell. What is electrochemical cell? Electrochemical cell, it consists of two electrodes in contact with an electrolyte. Let's write the definition. Consists of two electrodes in contact with an electrolyte. In simple terms, we can define electrochemical cell as two electrodes connected together. They are connected together using a conducting wire and a salt bridge. Let's draw an electrochemical cell. This is an electrochemical cell. Copper, and this metal as zinc. And this is metal and metal ion electrodes. And the solution contains ZnSO4, zinc sulfate, and the 1 mole Gm-3. And here it contains copper sulfate, CuSO4, 1 mole Tm-3. This is the salt bridge. This is the salt bridge, and the salt bridge can be NO3, KNO3, and potassium chloride. These are electrolytes, and at the end of the salt bridge, there will be jellified agar or cotton wool. It is used as a stopper. This helps to prevent mixing of the contents. This prevents mixing of contents in the salt bridge with the contents in the two beakers. Let's write it down. Cotton or agar. This is the electrochemical cell. There will be a potential gradient between the electrolytes. Electrolytes means the liquid present inside the electrode. Potential generated. Potential generated due to presence of two different electrolyte in electrode compartment, and this potential is reduced by the salt bridge by connecting them using the salt bridge. Liquid junction is called as liquid junction, and this potential is reduced by this potential that created is reduced by salt bridge. And also the liquid junction can be made by permeable membrane, diaphragm, or porous partition. Let's write it down. Liquid junction also can be made by permeable membrane, diaphragm, and porous partitioning. These allow passing ions. If we consider this electrochemical cell, there are two half cells, and now we're gonna look at the equilibrium reactions of the half cells. Equilibrium reactions of the half cell. equilibrium reactions. The first, zinc 2 plus 2 electrons, they form zinc solid. And copper 2 plus 2 electrons, they form copper solid. The reduction potential, the standard reduction potential of zinc is equal to minus 0.76 volts, and standard electrode potential of copper is plus 0.34 volts. This minus sign represents that the zinc releases electron more readily than the hydrogen. The zinc release more electron readily than the hydrogen. The plus sign in the electrode potential of copper represents that the copper releases electron less readily than the hydrogen. Now we can compare the equilibria. Here this zinc, it is a minus sign. It releases electron. It should release electron. Therefore, the equilibrium should be shifted to left side. Copper has the positive potential, therefore it should gain electron. So the equilibria favors right side to copper and left side to zinc. We have already learned this. More negative means more negative, release electron. More positive means gain electron. Standard reduction potential, if the standard reduction potential is more negative, it release electrons. If it's more positive, it gain electrons. In electrochemical series, when there is more electron will flow from high electron concentrated area to low electron concentrated area. Here we saw there is more electron in zinc. Therefore, the electrons will travel from zinc electrode to copper electrode. Here the equilibrium shift to left side, and here the equilibrium shift to right side. Therefore, the zinc solid will break into zinc 2 plus and electrons, and these electrons will react with copper 2 plus. These 2 electrons released are these electrons. These electrons react with copper 2 plus and form copper solid. I'll repeat it again. Here the zinc is undergoing oxidation reaction. So the zinc here, zinc will form zinc 2 plus aqueous plus 2 electrons, and here the copper 2 plus aqueous plus 2 electrons. These 2 electrons will come here. 2 electrons, they form copper solid. Net flow of electron will be from zinc to copper. When electrons from zinc travels to copper, a current is produced. A current travels in opposite direction of electrons. Here the current is produced spontaneously due to the chemical reaction. Occurrence of chemical reaction is spontaneous, and therefore it is possible we can divide the electrochemical cell into 2 types. First, galvanic cell or voltaic cell, which is spontaneous. If the chemical reaction occurs spontaneously, it is known as the electrochemical cell is known as galvanic cell or voltaic cell. If the reaction is not spontaneous, it is electrolytic cell. For electrolytic cell, there should be an external source of current that should be supplied to operate. There are 2 types of cells. First, galvanic cell, and second, electrolytic cell. In galvanic cell, the galvanic cell is called as voltaic cell. In galvanic cell, the electricity is produced spontaneously. Electricity is produced spontaneously. An electrolyte in electrolytic cell, electricity is produced, but it is non-spontaneous. We need to supply external current should be applied. In galvanic cell, oxidization takes place at anode. Oxidization takes place at anode. And reduction takes place at cathode. And anode carries a charge sign negative, and cathode carries a sign positive. If an external opposite potential is applied to galvanic cell, the potential increase slowly, and the reaction continues and takes places till the opposite voltage reaches certain value. When the reaction stops, although there will be no currents, and any further increase in the external potential start the reaction, but in opposite direction. The reactions will be in opposite direction, and that cell is called as electrolytic cell. If a potential is supplied to a galvanic cell, sufficient potential is supplied to galvanic cell, or external current is supplied to a galvanic cell, it will be turning into electrolytic cell. Let's take anode and cathode. Anode undergo oxidization. Cathode undergo reduction, and the potential will be negative in anode, negative potential, and cathode will be positive potential. Electrons will be moving from negative terminal to positive terminal. Electrons will be moving from negative terminal to movement of electrons. What is cell potential? Cell potential is the potential difference between two electrodes in a galvanic cell. The potential difference between the electrodes of the galvanic cell. And also the cell potential is called as electromotive force, which is EMF, electromotive force. Okay, let's write it down. Cell potential, electromotive force. It is the potential difference between anode and cathode. Potential difference between anode and cathode. The next one is liquid junction potential. What is liquid junction potential? If there is an electrochemical cell where two electrodes are in two different electrolytic solution, If there are two different electrolyte solution, and there will be an additional potential difference arise across the boundary, and that arising the arising potential is called as liquid junction potential. Let's write it down. If the electrodes are placed in different electrolyte, there will be a potential arise that is called as liquid junction potential, and this liquid junction potential is minimized using the salt bridge. Salt bridge contains KNO3 and KCl. Salt bridge reduces liquid junction potential. There are some important points when writing the cell notation. Okay, let's first, interfaces should be separated by vertical line. Always oxidization half reaction should be written in left hand sided, and the electrode with reduction half reaction should be written in right hand side. Let's write and look at the other points. Cell notation rules. Rules of cell notation. Rules of cell notation. First rule, electrolyte and metal should be separated by vertical line. Should be separated by a vertical line. That is first one. Second one, the salt bridge should be indicated as double vertical line. Double vertical line. The third one is oxidization half reaction. Should be in left side, and reduction half reaction should be in right side. If a liquid junction is present, fourth one, if a liquid junction present, it should be presented in dotted lines. Liquid junction is present should be used marked as dotted line in between the electrodes. There can be either liquid junction potential or salt bridge. If liquid junction potential, we should mark it as dotted lines. If the salt bridge is present, we should mark it as double vertical line. The fifth one, physical states must be mentioned. Physical states must be mentioned. Concentration, pressure, temperature must be mentioned if given. If a cell contains zinc and copper, and zinc electrochemical cell, it is called as Daniell cell. Sorry, I missed the electrolytic part. In electrolytic cell, anode and there will be a cathode. The oxidization will occur in anode, same as galvanic cell. Here the cathode will occur in the reduction, but anode will have a positive terminal, positive potential, and cathode will have a negative potential. If we consider this third point, I'll explain this using Daniell cell. If we consider copper and zinc as electrodes, zinc 2 plus aqueous plus 2 electrons forms zinc, and the electrode potential is equal minus 0.76 volt, and copper 2 plus aqueous plus 2 electrons, they form copper solid. Electrode potential is plus 0.34 voltage. How can we find which is anode and which is cathode? By comparing the values of electrode potential. Electrode with less electrode potential means negative electrode potential is anode. Therefore, the zinc electrode will be anode, and higher electrode potential, that will be cathode. Here we are talking about galvanic cell. This solid, after the cell notation, it is about galvanic cell. And anode undergo, this is minus means it should give electrons, therefore it undergo oxidization. Anode undergo oxidization, and cathode is positive terminal, therefore it should undergo reduction. It absorb electrons, it gain electrons. Let's write the reaction from the beginning. Zinc solid is converted to zinc 2 plus aqueous plus 2 electrons, and then the copper 2 plus, and these two electrons form copper solid. To write the cell notation, we should go like this from here, and then this. We should go like this to write the cell notation. Here first there is zinc. Zinc means anode. We should start from anode. A is the alphabet. Anode A. We should start from anode. Zinc solid. There is an interface and zinc 2 plus aqueous, and there will be a salt bridge and Cu2 plus aqueous, and this one is okay, done. We have written this, and written this, and the next one is copper solid. This is a cell notation. And now let's look at EMF of the cell. How can we find the EMF of the cell? EMF equal to EMF of the cathode minus EMF of anode. Let's find the EMF of the Daniell cell. Here we know the cathode has plus 0.34 plus 0.34 plus 0.34 voltage minus, and here the anode has minus 0.76 voltage, minus and minus 0.76 voltage, and this will be plus 0.34 plus 0.76. The answer will be 1.1 voltage, and it is plus 1.1 voltage. The sign should be mentioned. We can write the cell notation using this flow, and solid should release an electron, and that electron should be gained by an ion, and it should form a solid. Anode will release electrons, cathode will absorb electrons or gain electrons. Now let's discuss about factors affecting the electrode potential. Factors affecting the electrode potential. Factors affecting the electrode potential. There are 5 factors that affects the electrode potential. The first factor is temperature. First factor is temperature, and the second one is concentration of the electrolyte concentration. The third factor is nature of the electrolyte, and the fourth one is pressure of the gas, and the last one is fifth one, type of electrolyte. Okay, now let's discuss about different types of electrochemical cell. Different types of electrochemical cell. Different types of electrochemical cells. Electrochemical cells are used to convert chemical energy into electrical energy. And there are primary cell and secondary cell. Primary cell and secondary cell. In primary cell, the cell reaction cannot be reversed by providing an electrical energy. Cell reaction cannot be reversed by providing electrical energy. But the secondary cells are rechargeable. This can cell reaction can be cell reaction can be reversed electrically. This means it is rechargeable. These batteries are rechargeable cell, and this is not rechargeable, non-rechargeable. Examples: normal Legendre cell, B Daniel cell. Here the secondary cell lead accumulator batteries. Lead accumulator, which is car battery. This is the normal Legendre cell and the Daniel cell. This is the summary of different types of electrochemical cells and their electrolytes, positive pole, negative pole, and their cathode reaction and anode reaction, cell reactions are given. You can take a screenshot now. We learned about galvanic cell. That's all for galvanic cell. Discuss about electrolysis, the last part of electrochemistry. What is electrolysis? In previous lesson, we learned that the electrolytic cell means it is non-spontaneous. The chemical reaction of electrolytic cells are non-spontaneous. We should supply electrical energy for the reaction. Electrolysis is conducting a non-spontaneous chemical reaction using electrical energy from the outside. Let's write it down. What is electrolysis? Electrolysis means conducting a non-spontaneous chemical reaction using electrical energy from external source is called as electrolysis. In electrolysis, the electrode that is connected to positive terminal of the external source of electricity is positive electrode, which is anode, and the electrode which is connected to negative terminal of the electric source is negative electrode, which is cathode. Let's write it down. Electrode connected to positive terminal. Here the electrode connected to negative terminal of external source. If it's connected to positive terminal, it will be positive electrode. And if it's connected to negative terminal, it will be negative electrode. And the positive electrode is known as anode. And the negative electrode is known as cathode. Here the oxidation reaction and reduction reaction is opposite to galvanic cell. In galvanic cell, in an reduction occurs. In cathode, oxidation occurs. But here in electrolysis, in anode, oxidation occurs. In cathode, reduction occurs. The first part of electrolysis is electrolysis of water. Electrolysis of water. Electrolysis of water is not spontaneous at standard temperature and pressure. Therefore, in order to electrolyze water, we should supply external electrical energy. Let's write it down, not non-spontaneous in standard temperature and pressure. Therefore, we need to supply external electrical energy. And when the external electrical energy is supplied, electrolysis of water occurs. Now let's look at the experimental setup of electrolysis of water. This is the setup of electrolysis of water, and this green color is the wire, conducting wire, which is connected to a electrical source. And this is a solution which is sulfuric acid H2SO4, diluted H2SO4 solution. Here there will be O2 gas produced, and here it will be H2 gas. And these are boiling tubes. These were the boiling tubes, and this is a stopper. And these are, both of these are platinum wires. Platinum wire. Batteries terminals should be interchanged, and this is plus terminal, and this is minus terminal. This is positive terminal, and this is negative terminal. The main ionic species of pure water is H plus and OH minus. H plus ions and OH minus ions. The dilute H2SO4 is added to water to enrich H plus in the solution. When H2SO4 added, the H plus concentration will increase. Increasing in H plus concentration facilitates conduction of electricity. Conduction of electricity. Let's note it down. H2SO4 is added, diluted H2SO4 is added to H2O to increase H plus ions. Now let's look at the reactions in anode. In anode means the positive electrode. Positive electrode means the electrode which is connected to positive terminal, and so this is anode. Anode, and this is cathode, which is connected to negative terminal. In anode, oxidization occurs. Oxidization. Anode oxidization. Let's look at the oxidization reaction. H2O to H2O liquid forms O2 gas plus 4H plus aqueous and 4 electrons. And in cathode reduction reaction occurs. Reduction. Four H plus 4 electron, they form 2H2 gas. If you consider the overall reaction is 2H2O liquid forms 2H2 gas plus O2 gas. If we look at the overall reaction, we can say that the H2O concentration does not affect the electrolysis. We can find the minimum voltage required for electrolysis of water using that E cell equal E cathode, cathode minus electrode potential of anode, using that equation. And anode oxidation occurs in H2O breaks into O2 and 4H plus. For that reaction, the electrode potential is 1.23 voltage. For formation of H plus electrode potential is 0. Standard hydrogen electrode. This is standard hydrogen electrode. And if we consider those, here cathode is 0 voltage minus 1.23 voltage. Therefore, the E cell should be minimum voltage should be 1.23 voltage. When the E cell elect potential, when the potential of the cell is negative, if it's negative, delta G will be positive. Delta G will be positive. External electrical supply should be minimum of 1.23 voltages. Now let's look at electrolysis of copper sulfate using copper electrodes. Electrolysis of copper sulfate using copper electrodes. This is used to purify copper. Used to purify copper. The raw copper is extracted from ore using carbon. However, there is many impurities. Therefore, the pure copper can be obtained when the copper sulfate solution is electrolyzed. Here the positive electrode will be impure copper and negative electrode will be pure copper. Let's write them down. Anode, which is positive terminal, positive electrode is impure copper. And the cathode which is negative electrode, which is pure copper. And we know that in anode oxidation occurs and in cathode reduction occurs in electrolysis. Impure copper rod will dissolve and provide copper 2 plus ions to the solution, and while the more copper solid will deposit on the pure copper and grow its size. The cathode size will grow. Let's look at the reactions. In anode reaction, let's look at the anode reaction. Anode reaction, copper solid will form Cu2 plus aqueous plus 2 electrons. Here the cathode, which reduction occurs, Cu2 plus aqueous plus 2 electrons, they form copper solid. Here oxidation occurs. Here in cathode reduction. Now let's look at the experimental setup of electrolysis of copper sulfate using copper rods, using copper electrodes. This is the experimental setup, and these are dipped in CuSO4 aqueous, and this is pure copper, and this is impure copper with impurity, and they are connected using a wire, and the positive terminal, and this is negative terminal. Positive terminal is anode, and the negative terminal is cathode. Anode, and this is cathode. The copper in the impure, they release into aqueous solution Cu2 plus, and these Cu2 plus will form attach, and this is the newly formed. This is copper depositions. Copper depositions. Okay, the next part is electrolysis of copper sulfate using inert electrodes. Electrodes are inert electrodes. We use electrodes such as inert. In this case, we use inert electrodes. Inert electrodes are used. Example, we can take platinum and graphite. Now let's look at the reactions in anode and reaction in cathode. Here the anode release O2 gas. Anode releases O2 gas, and cathode deposition of O2 gas and deposition of copper. Copper deposition occurs in cathode. And now let's look at the reaction. Anode reaction. H2O liquid forms O2 gas plus H plus and electrons. If we balance these 4, and this should be 2, and this is aqueous. And if we take the cathode reaction, cathode will be the ions in the aqueous solution Cu2 plus aqueous plus the 2 electrons, and the copper solid will form. And the overall reaction is, take the overall reaction 2 Cu2 plus aqueous plus 2 H2O liquid forms 2 copper solid plus O2 gas plus 4H plus aqueous. We can find the standard electrode potential using the table. Using the standard reaction potential table in the exams, they will give us the standard electron potential. Here, oxidation of water is more feasible than the oxidation of sulfates. Here, oxidation of water is more feasible than oxidation of sulfate ions. Therefore, at the anode, O2 gas will be released by oxidation of water. Let's write down. Oxidation of water is more feasible than oxidation of sulfate ions. Therefore, O2 released by H2O. Oxidation of H2O. Now let's discuss about electrolysis of sodium chloride using inert electrodes. When considering electrolysis of sodium chloride solution, it is important to analyze the oxidation and reduction reaction that can happen in corresponding to the electrode first. And then the comparison of the standard reduction potential of the reactions can be used to predict the product. First, we should find which electrode undergo oxidation and which electrode undergo reduction. By comparing them, we can predict the final product. Now let's look at the reactions of electrolysis of sodium chloride. First, H plus gas, H plus aqueous plus 2 electrons, they form H2 gas. Is 2, and the second reaction is 2H2O liquid plus 2 electrons and 2H2 gas, sorry, H2 gas plus 2 OH minus aqueous. The next one is Na plus aqueous plus electron forms Na solid. And if we consider the reduction potential of these, reduction potential of hydrogen is 0 voltage. Reduction potential of H2O is equal minus 0.83 voltage, minus 0.83 voltage. And the next one is equal minus 2.71 sodium voltage, 0.83 voltage minus. Okay, when we consider the standard reduction potential, the most probable reduction reaction is the first reaction, but the H plus concentration is very low, therefore it is not possible under laboratory conditions. And if we consider the third one, it is very large negative potential. Third one has a very large negative reduction potential. Therefore, we can guess that the most possible reduction reaction is the second one. I'll mark the number. This is first reaction, second reaction, and the third reaction. Okay, let's look at these. Okay, let's write the reasons. First reaction. Okay, let's write these are reduction reactions. Possible reduction reaction. First reaction cannot occur due to low H plus concentration. The third cannot occur due to large negative reduction potential. Second one, more suitable. Now let's look at the oxidation reaction. We should determine the oxidation reaction. There are two oxidation reactions. Let's look at those. Okay, now let's look at the oxidation reaction. Possible oxidation reaction. The first one is first reaction, Cl minus 2Cl minus aqueous, and it forms Cl2 gas and 2 electrons, and 2H2O liquid forms O2 gas plus 4H plus aqueous and plus 4 electrons. Let's consider this as fourth reaction and this as fifth reaction. Fifth reaction. We should consider the reduction potential. We should consider the reduction potential of these. Okay, reduction potential of reaction fourth and fifth. And reduction potential Cl2 gas plus 2 electrons, they form 2 Cl minus aqueous. And the fifth reaction, this is fourth one, and fifth one, O2 gas plus 4 H plus aqueous plus 4 electrons, they form 2H2O gas, the fifth one. And the electrode potential, sorry, reduction potential of fourth reaction is plus 1.36 voltage, and reduction potential of water is, the fifth reaction is plus 1.23 voltages. If we consider these two reactions, the fourth and fifth reaction, the fourth reaction is more feasible than fifth one. According to the reduction potential, most favorable oxidation state is fifth. However, when the experiment is conducted, gas evolved is Cl2 but not O2. It is something called as, the reason for this is something called as overpotential. It is not in our syllabus. Let's look at it after writing notes. Let's write it down. Fourth reaction is more feasible than fifth. Therefore, according to the standard reduction potential, the four most favorable oxidation reaction is fifth one. If we compare these two, the electrode potential, the reduction potential of the fourth reaction is higher than the reduction potential of fifth. Fourth reaction undergo reduction quickly, but here we need to find the which undergoes oxidation quickly. Therefore, the fifth reaction is more suitable. Okay, now let's look at what is overpotential. Due to overpotential, gas evolved is Cl2, not O2. This means the fourth reaction is occurring here. This is because of the actual potential that need to be supplied for the reaction to take place is sometimes greater than the standard reduction potential. What is overpotential? Let's write it down. Actual potential needed to be actual potential needed to be supplied E supplied for the reaction to take place is sometimes greater than the standard potential. The detailed discussion of these is not in our syllabus. And in other words, we can say that standard reduction potential can be used to obtain minimum voltage values. Standard potential can be used to obtain minimum voltage values that can be supplied to drive an reaction of interest. Minimum voltage to drive the reaction. However, actual voltage may be higher due to presence of overpotentials. In this case, therefore, the Cl2 gas is released because the overpotential of reaction 5 releases O2 could be much greater than the reaction 4, and thus the reaction requires less potential to be supplied for the reaction 5. Therefore, the reaction 4 requires less potential to be supplied than the reaction 5. This is due to over potential. Now let's look at the reactions here. Anode reaction undergo oxidization, and the reaction is 2Cl minus aqueous forms Cl2 gas plus 2 electrons, and the cathode reaction is cathode reaction undergo reduction, and the reaction is 2H2O liquid plus 2 electrons. They form H2 gas plus 2 OH minus aqueous. The overall reaction is 2Cl minus aqueous plus 2H2O liquid forms Cl2 gas plus H2 gas plus 2 OH minus aqueous. And that's all for sodium chloride, electrolysis of sodium chloride using inert electrodes. Now let's look at electrolysis of sodium chloride, which is molten liquid sodium chloride, using inert electrodes. Now let's discuss about electrolysis of molten sodium chloride using inert electrodes. At room temperature, sodium chloride is solid and it does not have any mobile electron, therefore it does not conduct electricity. The solid sodium chloride does not conduct electricity due to absence of mobile ionic species. And when the temperature is raised beyond the melting point, the molten sodium chloride is produced, and it contains sodium plus ions and Cl minus ions. And electrolysis of molten sodium chloride will result reduction of Na plus ions to Na solid, and Cl2 gas is also produced as oxidation product. Let's write them down. For sodium chloride solid, heated, and sodium chloride liquid, and liquid contain Na plus ions plus Cl minus aqueous, and this Na plus electron forms Na solid, and this Cl2 minus 2Cl2 minus forms Cl2 gas plus 2 electrons. Here this is the equation. This is cathode. Reduction occurs here, and this is anode, oxidization. And if we consider the overall reaction, 2Cl minus aqueous plus 2 Na liquid, Na plus liquid, and they form Cl2 gas plus Na liquid. Sorry, this should be liquid, right? This is liquid, and this is also liquid. This is also liquid. Here Cl2 is also liquid. This is also liquid. This one is also liquid. Sorry about that. Industrially, sodium metal is extracted by electrolyzing molten sodium chloride solution. An industrial setup is known as down cell. They call it as down cell. Industrial in a metal is extracted by this method. They call this as down cell. They call this as down cell. Now let's discuss about quantitative aspects of electrolysis. The first scientist who described the quantitative aspects of electrolysis is Michael Faraday. There are two laws for electrolysis. There are two Faraday's law for electrolysis. Let's write it down. Faraday's laws by Michael Faraday. His first law was the amount of chemical reaction which occurs at any electrode during the electrolysis by a current is proportional to the quantities of electricity passed through the electrolyte, which can be a solution or melt state. Amount of chemical reaction which occurs at any electrode during the electrolysis by a current is proportional to the quantities of electricity passed through the electrolyte. Let's write it down in simple terms. First law. Amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through electrolyte. The amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through the electrolyte. Okay, the second law of Faraday is the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Let's try them in simple terms. Amount of different substances liberated. Amount of different substances liberated by same quantity of electricity passing through the electrolytic solution is directly proportional to their chemical equivalent weights. Their chemical equivalent weights. Their chemical equivalent weights. The first law is the amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through the electrolyte. The second law, amount of different substances liberated by the same quantity of electricity passing through the electrolyte is directly proportional to the chemical equivalent weight. What is chemical equivalent weight? Chemical equivalent weight means AMU, atomic mass unit, divided by number of electrons required to reduce cathode. The quantity of electricity passed can be given as Q equal IT. Q means charge, I means current, T means time. The amount of current required for oxidation or reduction depends on the stoichiometry of electrode reaction. Let's write it down. Amount of electricity, or we can take it as charge needed for redox oxidation or reduction reactions depends on stoichiometry of chemical reaction. The quantity of electricity is called as Faraday. Quantity of electricity is Faraday, which is a constant. It's a constant. And 1 Faraday is approximately equal to 1 Faraday, which is symbolized by capital F, is approximately equal to 96,500 coulombs per mole. For example, if we consider magnesium 2 plus, if we need to reduce this, we need 2 electrons and it will form a magnesium. Here we need 2 moles of electron. 2 moles of electron. To reduce magnesium 2 plus ion into F equal to F. Let's look at the application of Faraday's constant, and we multiply current, which is amperes, into time in second. It gives us coulombs, which is charge, coulombs, C, and coulombs are converted into moles of electrons, and moles of electron, moles of product or reactants, Here we can multiply the current into time and find the charge, now amount of charge and amount of coulombs, and you can divide the coulombs by the moles and find the moles of the product and moles of the reactants. The last part is comparison. We already compared the galvanic cell and electrolytic cell. Let's look at it again. Here it is. galvanic cell and electrolytic cell.
In galvanic cell, electricity is produced spontaneously, but in electrolytic cell, the electricity is produced non-spontaneously. Therefore, an external current should be supplied for electrolytic cell.
And difference between anode and cathode, if we take the anode and cathode, both of them are anode undergo oxidization and cathode undergo reduction in both, but the terminals are different. Here in galvanic cell, the negative potential for anode and positive potential for cathode, and the movement of electron from anode to cathode. In electrolytic cell, anode is positive potential and cathode is negative potential. That's all for electrochemistry. I hope you guys understood. Thanks for watching.